time so that we can, during our break, have a bit more time just for short discussions about this. So the first talk is Aloni Cohen from Massachusetts Institute of Technology towards formalizing the GDPR notion of singling out.
Hi, welcome. Thanks to the organizers for inviting me. So I'm going to tell you about this work, joint work with Kobe, towards formalizing GDPR notion of singling out. The paper is not online, but if you want to see it, you can send us an email and we'll send you a draft. And the first thing to say is that this is not a talk about differential privacy. It will involve differential privacy, but this is not a DP talk. So we heard more on the first day about data privacy laws. And the laws, if we listen to Alex or Felix, tells us that you must do some things ABC, like Title 13, which governs the census, GDPR in Europe. And then there's techniques from either from statistical disclosure limitation or cryptography or whatever. And this basic question of do the techniques satisfy the laws? How do they help you achieve them? And so this is a question that is important, and people, does this thing need to be on, or is it just for the live stream? Okay, we're good. Okay, I can't hear anything. So this is a table from a document, which we'll return to at the end. But I just wanted to flash it. This Article 21 Working Party opinion. It's about GDPR and certain types of privacy attacks. And they ask this type of question. Here are some techniques. Here are certain types of attacks. And they say things like K-anonymity prevents singling out attacks. And differential privacy might not prevent singling out attacks. So this is the type of question that we want to ask. But underlying these claims, these are a bunch of claims we think are technical, are mathematical ideas. Those are not just legal claims. This is extremely loud, I think. No? Yeah. Not just legal ideas, but there are mathematical ideas in those claims. And so what we want to do is we want to do a sort of a legal and mathematical analysis. So start with, so this is sort of the outline of the process. Start with the text of the law or some guiding documents, opinions about what the law means, and try to extract from it something useful that's formal and mathematical. Analyze the formal mathematical thing, and what properties does that concept have? How does it relate to other concepts, mathematical concepts? And then we want to take it back to the legal regime. So we want to be able to draw legal conclusions. And so no one of these steps is the important part. It's sort of the fact that we're trying to do the whole circle, which is what we think is the important part. And so there is some earlier work with a lot of authors, probably half of them are at the workshop, doing something similar for FERPA. And I'm not going to talk about it more. So in this work, we're looking at a concept called singling out, which comes from the GDPR. And related, Alex sort of alluded to it on Monday. We think it's related to some concepts of like distinguishability that is found in other privacy laws. But for the sake of this, I'm just going to talk about its relationship to GDPR. And so the legal concept of singling out, and we extract from it something that we call predicate singling out. It's a type of attack. And the security notion or privacy notion, which is security against predicate singling out, like I said, analyze its properties and its relationship to other notions, and then try to draw conclusions. So this is conveniently also the outline of the talk. So let's start with the first step. And you interrupt, and ask any questions you want at any time. So the GDPR, Article 1 of the GDPR, it's the first part, says that the regulation lays down rules with regards to the processing of personal data. And recital 26, a recital is like a preamble sort of, I think about it as like the preamble to the Constitution or something. It's part of the document, but it's not an article. So recital 26 says that the regulation should not apply, the restrictions should not apply to personal data that's been rendered anonymous. So what does this tell us? It tells us first that if it's not personal data, whatever data you're using, if it's not personal data, it's not under the purview of the GDPR. And this seems to be something that is pretty well accepted. At least that seems pretty well accepted. The recital 26 tells us something, like it suggests that there's something called rendering anonymous that one might do to personal data. So maybe you can take personal data and feed it through some magic box, and out comes something that's rendered anonymous. And the question that the setting of this work is, what properties do we need from this magic box so that its output can be considered anonymous and not be personal data and therefore not be under GDPR restriction? Yeah.
You're still looking just at M, not M of X. Like you're not saying what is the kind of X's under which these kinds of M produce M of X.
Yeah, we're just going to focus on M. Yeah. When did we start? Just so I know what the time is.
I'll let you know.
Okay, I'll keep track.
That clock is running.
Okay. So we have to understand what this personal data means in order to answer this question. So Article 4 of the GDPR says that personal data is any information relating to an identified or identifiable natural person, like we saw on Monday, sort of a circular, unclear definition. And the recital gives us a little more. It says that when thinking about what's identifiable, what identifiable means, account should be taken of all the means reasonably likely to be used, such as singling out to identify the person. So this, such as singling out, is sort of the only clarification, the only concrete hint in the text of the GDPR as to what identifiable means. So singling out is one way to identify. If identification is the big thing, singling out is one part of it. There are other things you can do to single out, which you see in other places, not in the text of the GDPR. But at least anonymization must prevent singling out. Whatever anonymization is and whatever singling out is, anonymization must prevent it. So Article 20, now we have to understand what singling out is. So we're going to turn to Article 29, Working Party Opinion on the concept of personal data. These working party opinions are some sort of official guiding document about the law. It turns out this working party opinion was written with regards to a predecessor of the GDPR, but the relevant parts are thought, we think, and as far as we can tell, other people think, hold over to the understanding of the GDPR. So it says that a person is identified within a group of persons when he or she is distinguished from all of the members from a group, for example, by specifying some criteria which allows you to narrow down the possible individuals to a single person. Okay, does that make sense? So you have the personal data. Here's some collection of criteria. Is wearing a long sleeve white shirt and jeans and is presenting at the Simon's workshop. And there's only one person in this room at this moment that satisfies that. Right? We're going to call this thing isolation. So some previous work, this is a paper by Francis et al. And another article with 21 Working Party Opinion. They understand singling out to be the same as isolation, and we're gonna diverge from this interpretation. And other things we get, I'm not going to put quotes, but other things we get from this document is that this set of criteria doesn't have to contain PII. It doesn't have to have your name or your email. It can be things that are just features about you. It could be some large set of properties that only one person satisfies. They're worried about, or they're considering a data that is anonymous can take any form. It doesn't just have to be microdata. It can be statistics. It could be like tabular data. And success is relative to a particular like group of people, a particular X. So the example they give is that a name might single out somebody in a room, but not in a country. So the room is X, and that's the set of people that were. Go ahead.
Good question. You mentioned that.
Can you speak up?
Can you hear me now?
Yeah.
So you mentioned that they're considering like statistics or tables, but maybe I misread this, but I thought that GDPR does not apply to statistical users of the data. So could you clarify?
Yeah. So just the first thing I should say is neither am I a lawyer, nor do I know almost anything about the GDPR that I'm not going to tell you in this talk. The second thing is that if I am a company and I have data from my, if I take data from my users, is it possible, like, can I compute things on that data and post it online? That's the question. So the answer to that is yes, if the thing that you computed is anonymous. The thing that I computed doesn't necessarily have to be microdata. I could also compute tables of, when my users are most likely to use my website. So I think that what you're talking about is statistical uses in the Census Statistical Agency's sense, but I don't know. The short answer to your question is I don't know. If that didn't answer it. Go ahead.
I think the clauses you're referring to when statistical agencies, if Gillian's doing it, it's statistical use. If you do it, it's not.
I see.
Yeah.
Got it. Thank you.
Good. Better answer. Thanks. Good. So now I'm actually not going to show you the slide. So the question is, so what is this weird singling out thing, and why should we care? Especially because you don't need to know the name you don't need to find the name of the person. This is a clip from a movie called Democracy, which is a documentary, which I think was screened here a month or so ago, about the creation of the GDPR. And here's this little, oh, you can't see anything, can you? I'm going to put it over here. Great. Now you can see it. Go. So hopefully sound and everything works. So she's asking, what's the difference between singling out and identification? Why do we care about singling out if you don't know the names? She's finishing her question.
So I can single out that there are lots of different people, but I can't identify any of them.
Now, in real life, in a classroom, the boy with the dark hair, curls, and the blue trouser, please leave the room. Then everybody knows who it is. This singling out refers to the capacity of providers on the internet. They're able to use the well-known attributes of this single user by nudging someone into behavior. That's effective advertising. They say, we don't know who this is. It's anonymous. No. The point is, it is personal data, without any doubt.
So this guy is the former something. Data protection, EU data protection supervisor, I think is the title. Head of the Dutch DPA, former head of the Article 29 Working Party opinion group. So anyway, singling out, I won't belabor it, but singling out we think can be a stepping stone to sort of greater harms, and re-identification also allows you to treat somebody differently and say the person with the blue trousers or whatever, you leave the room, even if you don't know that person's name. Good. So now we want to take the second step, which is to try to formalize some useful notion out of this. So let's start with isolation, which is where we were before. So isolation is when you say there's exactly one person in the data set that satisfies these attributes. And this is from that paper I mentioned earlier. So for example, here's some data set, a pretend sort of Netflix data set. So you can see there's exactly one person who rated the movie Crash a 4. There's exactly one person who watched Mulan between a certain set of dates. And there's only one person that doesn't satisfy the first two predicates. So each of the 3 rows in this table can be singled out, but can be, isolated by a predicate. Okay, so let's set the sort of syntactically what we're talking about. So X is going to be a data set drawn IID from some distribution, and the data set is of size n. So yes, IID data sets are not all the data sets in the world. but we're going to restrict our attention to this. I'll come back to that restriction later. So some distribution D, you pass it through this M, this is the anonymization mechanism, and you publish this output. We can think about also interactive mechanisms. Then there's this adversary who's the singling out adversary, wants to single out. What do? They output a predicate, and this predicate is tested against X, right? So the adversary's goal, if we want to formalize security against isolation as our notion, the adversary's goal is to output a predicate P that matches exactly one row in the data set. Clear? So here's the definition we could come up with. So the mechanism is secure against isolation if no adversary can do this, can isolate, except with negligible probability. Probability over X over M over A. And if you don't know what negligible means, it just means it's some formalization of extremely small. So this is a definition. So this sort of sounds good. Except there's a problem with it. It's impossible. So it's impossible because I can violate the definition no matter what M is. In particular, I can do it without even looking at the output of the mechanism. So here's an example. What I'm going to do, this is my attack. I'm going to output a predicate P star. This predicate P star matches 1 in n people in the distribution, right? So if there's 365 people in the data set, then my predicate might be is born on February 2nd. That matches about 1 in 365 people. And the probability that predicate isolates in the distribution is about 37%. So it's n times the probability that that hits on any one row is 1 in n, times the probability that the other n minus 1 rows don't get it. And this thing looks like 1 over e. These things cancel. It's about 37%. It doesn't depend on n. And the things to note are we can do this without even knowing anything much about the distribution, as long as the distribution has enough randomness. And that's a point I'm going to come back to eventually. So this attacker doesn't look at the mechanism. I'm going to call such an attacker a trivial attacker. Okay. Question?
Doesn't this depend on your ability to express a predicate that matches 1 over n fraction of the people?
Yes.
Because
Good.
The only thing
So
is that, like, you can.
Saying if the distribution doesn't even have support predicates that have this weight, yeah, great. You're right. There's an asterisk here. I'm going to get to it. But yes, you're right. But yeah, I'll get there. Is this example clear? But somehow this was like not that exciting. If you manage to isolate with this predicate, it's trivial in some sense. So what makes an attack not trivial? So if that was trivial, then maybe it would not be trivial if you use the same type of predicate, but you manage to isolate with probability 97% instead of 37%. Much better than this trivial baseline. Which sort of suggests that we have to compare success with respect to some sort of statistical trivial baseline. But 37 is not the absolute baseline, because I might be able to learn that somebody's a vegan Colombian Jewish pilot fluent in Dutch, which I can't say quite as well as John can say 308 million, however many. There you go. Thank you. So if you can find this predicate in the data set, there might be one person in the world that satisfies this predicate, and you manage to do it with 10% probability, you've learned something from the output of the mechanism. And somehow this strikes us as non-trivial. So the baseline has to depend somehow on how rare or how specific these predicates are. So let's make that intuition formal. For a predicate, I'm going to define its weight as the probability that if you draw a random person from the distribution, the person satisfies the predicate. Okay, that's what this weight of P. And the baseline is a function of n and this weight. It's the maximum probability that a trivial adversary, one that doesn't look at the output of the mechanism, manages to isolate, that's what this notation is, isolate the data set with the predicate, and also output this predicate with this weight. Okay? So what's the probability that a trivial adversary can isolate with predicates of a certain weight? What's the best probability that trivial adversaries can do it? And that's our baseline. So I'm going to claim, and this asterisk is related to the earlier asterisk. Yeah.
What if the probability in the baseline is taken over m? If the adversary doesn't even look at it?
It doesn't matter. It's going to be the same. You're right. Because our on the next slide, the definition is also going to be taken over m. Conceptually, this is going to be the same this is going to be the same probability space as our real adversary, who's not trivial. I think it's just, never thought to simplify away the m, even though I think you're right that it's equivalent. So the claim is that the best thing you can do is the trivial adversary can do, doesn't get to look at the data, or doesn't get to look at the output of the mechanism, is just output a predicate that has this weight. And just like before, it's going to succeed with probability n times w times 1 minus w to the n minus 1, which looks like this thing, where nw here, nw is the expected number of hits you get on the data set, in e to the minus nw. Okay, so what does this thing look like? It's maximized here at 1 over n. So this is graphed for n equals 50. It's maximized at 1 over n, where you reach 1 over e. That's 37%. And it's negligible when the weight gets too high, much bigger than log n over n, or when the weight itself is negligible. So like over here at this time. And that's the regime where we're going to restrict our attention to. Good. So now that we have some notion of this baseline, we know we want to compare against the baseline. Let's fix the definition. So the adversary's goal is to isolate with probability better than the statistical baseline, where the baseline is a function of the predicate's weight. Good. So this is probably the most notation-heavy slide. So if you stick with it. So here's a piece of notation, which is sort of the same as we saw before. The success probability of an adversary for a given distribution and a given mechanism and a given weight is the probability that the adversary isolates with the predicate, and that the weight of the predicate is less than this weight. So we're going to allow our adversary to output predicates up to some certain maximum weight. Anywhere he wants from 0 to w is allowed to do. And the mechanism is secure against predicate singling out, PSO secure. If for all negligible weight predicates, the success probability is negligible. Okay, so in the regime where W is negligible, we saw that the baseline was negligible. So as long as the baseline is negligible, the adversary shouldn't do more than negligible. We also consider a more general version of the definition where we allow the baseline to not be negligible, in which case we compare the adversary's success probability to the baseline, and we want to say that he doesn't do much better than e to the epsilon times the baseline plus some delta. And in that case, we'll say that it's epsilon delta w PSO secure, where w tells us what regime of weights. It's epsilon delta. It has this guarantee. We also consider sort of the other side of the regime of weights, high weight predicates. But I'm not going to talk about it for the rest of the time. So any questions? Any questions? Okay. So what we want to capture is some condition that's necessary for GDPR anonymization. So GDPR, if you're a GDPR anonymizer, you must prevent GDPR singling out. That's what we saw before. And so we want to draw this circle, this yellow circle. So if we think we have. And so if this is the relationship, if predicate security, if GDPR anonymizing implies PSO security, it means that negative results are the ones that are going to be the easiest to draw legal conclusions from. If it doesn't satisfy PSO security, it's not going to be a GDPR anonymizer. Make sense? So if this is the relationship we want, then restricting the scope of our definition also it doesn't really cause a problem. So this is where the fact that we restrict only to IID distributions is not so bad. Because if you're going to be a GDPR anonymizer in all the cases for all the data sets, at least you should be able to anonymize on distributions that are data sets that come from nice distributions. Also, data sets about which I have no auxiliary knowledge. You should at least be able to anonymize that in that case. And it might be that you might think that predicate security, PSO security is very strong, because the definition we gave, I sort of glossed over it, but it quantifies for all distributions. It wants security for all distributions and all adversaries, even unbounded computation and even non-uniform ones that know the distribution. So this is an extremely strong guarantee, and maybe the GDPR doesn't care about such adversaries. Or if the adversary knows the distribution and has more computing power than NSA, who cares, right? So maybe, but all of our negative results, all the negative results that are the ones that give us the strongest legal conclusions, work with a very weak adversary who doesn't know the distribution, just knows the distribution has some min entropy. So the negative, the goal of getting legal conclusions is sort of not threatened by that quantification if you look at the theorems themselves, the proofs of the theorems themselves. And so the last question is, maybe PSO security is too weak to be meaningful, right? If everything's PSO secure, then I'm not going to be able to do anything useful with it. And here, the main weakness is this subtlety that I ignored when Ashwin asked about it, which I'm going to talk about now. So here's the baseline that I wrote down, and they claim the trivial adversary just outputs a predicate of this weight. And so, like you said, maybe such a predicate doesn't even exist. There's a more subtle problem, and the more subtle problem is that the adversary, this trivial adversary, we're assuming he knows the distribution to such an extent that he can find such a predicate, even assuming that the predicate, this weight, can be represented under this distribution. Saying the adversary knows the distribution so well that it can find such a predicate. And maybe such an adversary who knows everything about the distribution has an inflated baseline. And we're comparing against something that's sort of artificially high, right? This is a subtlety. And so the answer to, question.
Can you go over that again about the inflated baseline?
Yeah. So we're saying our definition of security says that our real adversary can't do much better than the trivial adversary. If the trivial adversary can do very, very well, this is not a very strong notion. If we defined our trivial adversary, if we defined our baseline in some way, that the baseline was always 100%, this whole security notion would be vacuous, right? So there's a worry that if we define the baseline in some way that inflates it, makes it higher than it should be, whatever it should be means. Like by giving the trivial adversary knowledge of the distribution, which maybe a real adversary doesn't have knowledge of the distribution. Do you know the distribution that the Netflix data was drawn from? No. But if we let if you're comparing against a trivial adversary who knows the distribution, maybe it's an unfair comparison. You're not going to be able to do better, but for a stupid reason. Does that make sense? I don't want to dwell on it much more. So the answer to both of these issues is that we can take nasty distributions, ones that don't, as long as the distribution has sufficient min entropy, which is to say it's random enough. How much min entropy? A little more than log n. So if it has even a moderate amount of randomness, then we can hash it down to a smaller space, get a uniform distribution out of it. And this hashing just uses families of hash functions. You don't have to know anything about D. So you can do this without knowing the distribution and without knowing how to represent these predicates. You hash it, and then here you can represent these predicates. And this is also sort of the trick that underlies the fact that all our negative results have these simple uniform adversaries, that we don't have to know the distribution because we can usually apply left or right lemma. Okay, so the end of all that got very technical. It's going to get less technical. So if I lost everybody, you should come back. Are there any questions, though, before I continue? Okay. What's the time?
You have 10 minutes plus questions. So if people are asking in the middle questions.
Only 10 minutes. Wow. Okay. Okay. So now we want to ask, let's understand this notion. So here's a mechanism, the counting mechanism. Takes a predicate Q and outputs the number of rows that satisfy Q in the data set. Exact counts. Is this secure against singling out? Turns out it is. The proof, very briefly, proof idea is that this mechanism only has a few outputs. It only can output n+1 numbers. So your baseline, you can only do much better than the trivial adversary by a factor of n+1. And when your baseline is negligible, n times negligible is still negligible. Since I don't have much time, I'm going to go a bit quickly. So what if, a question that people often ask is, what if Q matches one row in the data set? Why doesn't this help you single out? Can anybody see the answer to that? Because I think it's important to make sure you understand why this doesn't help. Right, so if I can get exact counts, what if the exact count is 1? Can't I single out? Didn't I single out? So the answer to this is that to single out, we require that the predicate that you output has a very small baseline, which is to say the chance that it matches one person in the data set is extremely small. And we take randomness over the distribution. So if Q is such that if you output Q, you would have succeeded, then the chance that Q matches only one person in the data set is extremely small. So it's true that if you got a count of 1, you would succeed, but the chance that you got a count of 1 is negligible. I don't know, that probably wasn't fun. So now we can ask another question. Now that we know the counting mechanism is secure, we can ask about whether predicate security against predicate singling out composes. So if a bunch of mechanisms are individually PSO secure, is the collection of those mechanisms PSO secure? And the answer is no, even if you compose a little more than log n times. And we can use counting mechanisms to show a counterexample. So let's say this is the data set, and this index is called x1, x2. So the idea is if Q1, if the first predicate isolates a row, then we can learn all the bits of the row that was isolated. So how do we learn that bit? So let's say Q1 matches one row. This one, we don't know it's this one, but it's this one. Then Q2, we can ask Q1, and the first bit of x is 1. Right? So that predicate will either match 0 rows or 1 row, depending on whether this bit is 1. We can ask about the second bit. We can ask about the third bit. And we can go down. And after we learn enough bits, then we can specify, we can just start naming this row. And the weight of this predicate that we'll output goes down exponentially. So after you learn log n bits, you're set. And so, but this is all still conditioned on this if Q1 isolates x, right? Where do we get this Q1? But the trivial adversary is able to isolate a row with probability 1 over e, with probability 37%. So just output like this predicate from the trivial adversary. With probability 37%, it manages to isolate a row and then learn all the bits. You can amplify this to high probability, and you can even make it so that all the queries that you ask, all the queries that you get are high counts, not 0, 1 counts. So like low count suppression is not going to help you stop this sort of attack. I'm going to skip this example. It doesn't even compose twice. I'll leave it up while Ashwin asks the question. Go ahead.
The answer to my question, like, we all know that you can ask 2 counts and single out person, right?
What do you mean? Do you mean single out in the predicate singling out sense, or do you mean?
Like, it's a fraction attacks, right? So you can say how many people are there which satisfy some property, how many people are there which satisfies a sensitive property, in addition to the previous property. If the difference is 1, then you know that this person is there in your data set who has that thing. So
exactly. So this is. So this is, you're right, this is a differencing attack, essentially. This is a differencing attack that works without knowing anything about the data, without having any prior information, but also lets you discover these predicates without having any prior information. and also lets you discover a very low weight predicate that has a difference like this, a low predicate of negligible weight. But at the end of the day, there's just a difference, sort of an oblivious differencing attack happening here, if you want to think about it like that. I'm going to skip this example for time. So does predicate singling out security imply differential privacy? This one, I'm going to make somebody answer. You know the answer. Somebody knows the answer. No. Somebody said no. Why not?
It's deterministic.
It's not deterministic, but the example mechanism we just saw was deterministic. For example, an exact count is not differentially private, but gives you this PSO security. Turns out, though, that differential privacy does imply PSO security. For any epsilon bounded by a constant, and any weight between 0 and 1 over n, then epsilon delta DP mechanism gives you epsilon delta prime PSO security, where delta is negligible, the same, and epsilon is this thing, epsilon plus NW, which is bounded by epsilon plus 1. Right? But probably this NW is going to be much smaller than 1. So epsilon prime is like epsilon plus 1. And the way this thing is proved, okay, well, I really don't have time. The way this thing is proved is basically by observing that singling out is a type of overfitting in a way. That you have to output a predicate whose weight is W on the distribution, but whose weight is 1 in n, like matches one row in the data set. If W is much smaller than 1 in n, then the fit is like way better by a factor of 1 over n, which is not way better. But anyway, differential privacy prevents this sort of thing, and because I don't have time, I'm not going to tell you more about that. I want to talk about K-anonymity. So K-anonymity is something that has been brought up a lot, but I don't think has ever been defined or given an example. So here's a data set on the left, a 3 anonymous version of this data set on the right. So what's 3 anonymous mean? It means that on the right, every row on the left corresponds to 3 possible rows on the right. So you can't distinguish this row from this row just by looking on the right. So is this PSO secure? The answer is no. This particular K-anonymizer is not PSO secure. And why? Because you can look at this and you can say there's a 27 in the data set or a 343 in the data set. You can name rows, which allows you to output predicates of weight 2 to the minus n if your distribution is uniform, for example, which matches one row. Right? But this is a particular example. And when I presented this at TPDP, somebody was live tweeting it, and he said that K-anonymity doesn't prevent PSO security, doesn't guarantee PSO security if you don't pay attention to the borders of the buckets. But I think Ted got the wrong lesson out of this. So more generally, if we think about K-anonymity as outputting predicates, whatever these predicates are, and these predicates match K rows. And we think about the weights of these predicates as being extremely tiny, right? Because K-anonymity, you want to suppress as little as you can. You want the rows to be as specific as possible. So these predicates phi are very specific, have very low weight in the distribution. So there's an almost trivial attack. In the same way that the trivial adversary was able to get 1 row out of n, we can use the same idea to get 1 row out of k, right? So use the same sort of trivial attack on a chunk of k rows, and phi. So you output the predicate that says it's in this bucket, and it's 1 in k of these. So this predicate p has very low weight. It has weight less than phi, which we think is very low. And also it isolates within this chunk, sort of just like the trivial adversary. And actually proving that this happens, you have to use the conditional min entropy. So thank you, Adam, for writing that fuzzy extraction paper. It helped us. So it's a little subtle, but it works essentially just as well as the trivial attack. So I'm going to go a little, I'm finishing. So again, this is what we saw before. And what we want to do is we want to go from the technical results to the legal conclusions, right? We haven't tied the knot. We haven't done what we set out to do. So we think that PSO security is a stronger condition than preventing GDPR singling out. So what were our results? That K-anonymity doesn't provide PSO security. So the legal conclusion that we draw is that K-anonymity doesn't generically prevent GDPR singling out. This is in direct contradiction to the Article 29 Working Party opinion conclusion. Also, PSO security doesn't compose. So we think that on the legal side that GDPR is singling out probably also doesn't compose. And we think that this carries over because the counting mechanism, we think the exact count mechanism probably doesn't live in this little yellow space. So we think that non-composition also carries over to generally the concept of GDPR singling out. And finally, we know that DP is PSO secure, and it might be some evidence that it prevents GDPR singling out. Ultimately, we want to understand where GDP anonymization fits into this picture, but we don't. It could be sort of anywhere. Anyway, thank you. That's the end. Sorry for going a little over time.
Okay. We just want to make sure we have time for questions. So,
I have a question, and I don't mean this as a nitpick, but so like, I'm confused by your picture because some of these are like, some of these categories seem to be like about, definitions or something like that, but then composes is like a property of a definition, not of a...
Yeah,
so
I agree.
Okay.
I was thinking this to capture, this was going to be, it had a longer title, which was like security notions that compose or something. It satisfies a security property that self-composes. I think would be of the same type as this or this.
Okay, yeah.
But
that's fine. I had another question, but I've forgotten it, so I'll let them go. That's okay.
yes.
So you use, as a fundamental building block, you're using negligible functions.
yeah.
In crypto, I can see that always makes sense because these are functions in typically things like key length.
What's the complexity? Sorry, go ahead.
So you make these things as big as you need. But in this case, it was the size of the domains or the size of the data sets.
Size of the data set, yeah.
You don't have control over those. They are what they are. So, if I've got 100, I've got 100. So how do I interpret an asymptotic result when you don't have control over the parameters?
I think that's a good question. I think that the answer is probably that trying to formalize these concepts, we use the tools that are familiar and available to us as the first step in that process. So I don't know if you have a different answer to that.
You could choose concrete numbers in many of these places and get to roughly the same conclusions. When developing a theoretical concept, it's convenient to talk about subpolynomial functions as negligible. We could define n to the minus 10 as small enough for you and roughly the same theory will follow. Or you could even put tiny numbers there, 2 to the minus 40 or 80, and the same theory will follow.
The only place where the asymptotic really came in was this: we were restricting our attention. When we restricted our attention to weights that were negligible, or to the regime where the baseline was negligible. But the definition is at least well defined for the whole regime of baselines, where even when there's non-negligible, and you can talk about the concrete advantage you can get for predicates of, say, weight 10%. So I think there's nothing stopping one from doing a more concrete analysis of the same type of work.
Okay, any other questions? Okay, thank you, speaker. speaker is Christine Task, and my program I have TBA, so we'll see on your presentation. What the title is. What all we've been...
Yeah.